In this video, we're going to talk about how energy changes relate to reactions, chemical reactions. Often when a chemical reaction is written with respect to the energy change of the reaction, we call them thermochemical equations or thermochemical reactions. For example, the reaction given here. This is the reaction for the combustion of hydrogen, burning of hydrogen and oxygen. It's not balanced yet. In order to balance, let's see, I have 2 oxygens, I need 2 oxygens and 2 hydrogens. There we go. This balanced reaction represents the combustion of hydrogen. You may be familiar with combustion reactions. Basically, we're saying that hydrogen is burning in this reaction. It combines with oxygen, it forms liquid water, and a combustion reaction typically produces a flame. You see a flame. That is the amount of energy being given off. So there is energy released as this reaction proceeds. We call this an exothermic reaction because that amount of energy is being released. And we can actually calculate or determine how much energy is being released. And if we run this reaction, we find that the amount of energy being released is approximately 572 kilojoules. You look it up at different sources, you may see slightly different values for this, but this is a good agreed upon value. So I could write, so this is representing that exothermic reaction. I am writing the energy or the heat as part of the reaction. It is on the product side because it's being released, and here in this example I have given the actual numerical value for the amount that's being released. If I want to write the reaction backwards, for whatever reason, the 572 kilojoules of energy would be required to run the reaction this direction. In this direction, I would say that this is an endothermic reaction. This amount of heat is being absorbed during the process of the reaction. If you take Gen Chem 2, you learn about whether or not reactions are spontaneous, meaning, you can write anything you want, but does the reaction actually go? And you find out that this second way, that it's not actually spontaneous in this direction. I'll go ahead and get rid of this one, and let's look back at the one up above it. The exothermic reaction as written, this one is a spontaneous process. If you've ever seen a hydrogen balloon blow up, this is exactly what you were looking at. One thing to note is that the way that this reaction is balanced, there are 2 molecules of hydrogen and 2 molecules of water for every 1 molecule of oxygen, or we can state this in terms of moles. If I rewrite the reaction for whatever reason as hydrogen plus 1/2 of an oxygen, there's no such thing as a half of an oxygen molecule, but I could have half of a mole of oxygen. So essentially all I've done is I've divided all the coefficients by 2. The energy change now for the reaction written this way is half of what it was up above, or I would write it as 286 kilojoules. In this second reaction, I am expressing the amount of heat released for the reaction balanced as is. We can say that the delta H for this reaction is a negative, because that amount of heat is being released, 286 kilojoules as written. We would say that the delta H for this top reaction was negative 572 kilojoules, because as written it's being released, and 572 kilojoules are being released for it balanced the way it is. Or we could say that the delta H for this reaction is negative 286 kilojoules per mole of water, for example, or per mole of hydrogen, for example. Or we could say that it was negative 572 kilojoules per mole of oxygen, because there is 1 mole of oxygen written in this fashion. But essentially what we have here is we have a way to look at the stoichiometry of the reaction. In this bottom example, recall from chapter 4, moles, grams to moles, moles to moles, moles to grams. In this bottom example, we have some relationships, we have some molar relationships set up for us. In this bottom reaction, 1 mole of hydrogen gas, equals 286 kilojoules being released. You can actually have a negative sign here. It equals the release of 286 kilojoules or a negative 286. I'm just going to write it as absolute numerical values. So I could use that as a stoichiometric relationship. For example, if I wanted to know, well, if I have 10 grams of hydrogen, how much heat is going to be released? Well, how many kilojoules would be released from 10 grams of hydrogen? In order to get to kilojoules, I see I can use this relationship between hydrogen and kilojoules, but it's in moles, so the first thing I'll have to do is I'll have to go to moles. This is the molar mass from the periodic table. Then I'll need moles of hydrogen on bottom to cancel. I can put kilojoules on top. And I would get to three significant figures: 1,420 kilojoules of energy in the form of heat is released when I burn 10 grams of hydrogen. And so I can work a stoichiometry problem with this thermochemical equation, which I can relate grams and moles to kilojoules of energy based on this equation. And so I might need to do some stoichiometry again. Now, it is important to note that I have identified the physical state of each of these. And that's important because if I have different physical states, what I often find, or what I always find, is that it requires different amounts of energy. The delta H is different. For example, if instead I wrote the reaction, if I was going to gaseous water, I still need to balance it with the 2's here. This reaction releases a different amount of energy than the reaction that goes to liquid water. In this case, I get 484 kilojoules. So I do want to be a little bit careful about labeling states in this chapter. Whether I'm dealing with gases, liquids, solids, or aqueous solutions, it makes a difference. And just to kind of complete this, if I balance this reaction, I would see that for it balanced this bottom way, that it's only releasing 242 kilojoules, because again, it's this number written as part of the reaction is related to the mole-to-mole relationship between everything else. For this bottom reaction then, for the purple one, I would say that the delta H for this reaction is equal to negative 484 kilojoules. For the very bottom one, I would say that the delta H is equal to negative 242 kilojoules. Again, I could express it as 242 kilojoules per mole of water, or 484 kilojoules per mole of oxygen.